So in last CAM class, we were discussing about a new method for calculation of computational fluid dynamic like calculations, right? And the method that we discussed was finite volume method. So what I will do is let me just have a small recap, and if we can do some analysis in the meantime. So we'll have a small class. We anyways have a session. Acha, before starting that, okay, let me put this in here. Okay, share the screen. Right. Okay, so we were discussing this. We will discuss this. Before that, how many of us are here now? 14. So, few things before we start. Your lab journal for the last assignment, do submit those today. Uh, I think only 2 have submitted in that assignment part, so do submit those. Follow the lab assignment format, like lab journal, experiment number, date, aim, and how you solved it. Be precise, be unique, don't copy. So that will be helpful. Okay, each and every question has a certain answer to it. Like each problem has certain questions, so you ultimately have to find the answer. So that becomes easy. And आज के दिन submit कर दो तो that will be good, right? Next thing, after this, we have at 10:30 we have this lecture that is going to be presented by one of the startups founder. He's Mr. Arjun, and I think you might have got the mails and notification. So he is more into drone technology. So why we have invited him is because we are anyways working in computer applications in mining. So as an extension to that, and especially because field people are doing that, so this person will be has been working in this field for a long time, and he has actually recently in one of the conference I met him online. So he was presenting his work, and very nice work he has done about how the drone technology can be used in various aspects of mining engineering. So using drones to basically do various um, surveying works, estimation works, and optimization works, and how these can be, how the advanced technologies can be used to basically reduce our effort, reduce our cost, and make it more accurate. So in that ways, it will be very useful. So do be there after this. So that will do consider it as a part of your class only, because we will anyways cover that uh, remote sensing, and in remote sensing and all that will be covered. Some part of drone technology will be there. So today's this lecture or the talk that is organized. So do consider it as a part of the class and attend it accordingly. Okay. For you, do ask questions in relation to like in terms of the technical aspect. So because generally external speakers can be more into a business like of scenario. So even though he is the chief technical officer, so he's good in technical aspects as well. So do be technical as well as practical point of view. Do ask questions. Do inquire. I would highly encourage everyone to interact. because he's not like he's very young person, and this his startup is basically very recent and has been chosen as one of the top 5 startups in drone technology in the world. So that's a good thing. So good opportunity, and anyways, we are inclined in that direction to see how the technology can be used in our computer applications. So in mining applications. So be present at that. Okay. And the third thing, we are having a test as discussed last time. So it was supposed to be today, but since some of you requested, we are having it on Monday. So on Monday we will have the test at 3:15, the computer applications class. Okay. Uh, Only theory part, or the part that is not done on the simulation software, that all will be covered. So again, just to gist it out, we have flowcharts, we have algorithms, right? And we have the basics of what kind of estimation methods are there, finite element, limit equilibrium, what are its principles, and do go through the lectures, do go through the videos that are there. Uh, Most of the recent lectures or recent classes that we had were more into the demonstration part or the application part. So anyways, those are not covered. But this time we are not restricting to first 5 lectures or first 10 lectures or something like that. So have a look. Uh, Only the theory part is there. So do cover that completely. And will be limited till finite element method. So finite element, limit equilibrium, and flowcharts, algorithms, and anything that we have covered in the theory part as well in between. Okay. So questions will be again similar to last time. Uh, MCQs and short answer type questions, writing something. I don't think we have any major calculations in this course. So if there are there, then it will be short and not much. Be extensive in your study for flowcharts algorithms as well as these FEM and LEM methods, because questions will be there, and if you have not been thorough, then you might have missed some things. So do have a look. You have 3 days now because tomorrow also is probably a holiday, and day after Saturday and Sunday is there. So 3 days you are getting quite good buffer period. So use that. Okay. Anyways, so we'll have a very short class, and what I wanted to show you is an extension to what we were doing last time. This is a finite volume method that we were discussing last time. So when we compared it with the finite element, we discussed how with this in contrast to the calculations that were done on the nodes and the estimations were done in throughout the element, right, in finite element method. In contrast to that, the whole calculations are based on the full cell or volume. So that's why the name suggests as finite volume, right? And the principle behind finite volume method was seen that the conservation of material or flux. So conservation of anything, like whatever goes in comes out, and nothing can be created or destroyed. So like suppose whatever energy we are getting into a particular section of cell, suppose this cell is there, and whatever we are inputting, the same amount of output should be there. Condition is that it should not be a compressible material or a sink type of situation where heat absorption is there, or water can be compressed or so on. So in these conditions, if proper practical boundary conditions are there, So in that, by the conservation principle, whatever goes in, that comes out. So the summation of inlets or the summation of inputs is equal to the summation of the outputs. Or in terms of volume integral, the surface volume integral becomes 0, right? So that's the whole principle. Very simple calculations are there. Again, because we will be using softwares right now, and since we are not dedicating our effort in programming, because that's not the point here. So that's why it won't be much. The ease of this method won't be much apparent to us. It's because in simulation steps, while we do in our programming, it is very similar. But when we code these kind of situations, so coding becomes very easy, and especially in terms of fluids or fluid flow and heat flow or anything that relates to the conservation principle, which where it can be applied. So this method is useful, easy, quick, and quite accurate. Though the same thing can be done, again, I said with the same thing, same analysis, all the same things can be done by finite element method as well. We have seen that. But here is another method that is simpler to code, requires slightly less space or memory space, and calculations are quick. Okay, so that's why this method. Uh, So what we can do is either how much time we have, 15, 20 minutes. See, we will break at 10, 10, 10, like because I also have to arrange for that session. So 10:30 is the session. So we'll break at 10:10. Before that, I wanted to show you a few things. If I can do a very quickly CFD simulation, if that is possible. I don't know how much our system is uh, supporting us. So just a sec. Mm. Any questions in the meantime? You can have till the time I'm opening the software and all. Right. Okay. I think we can do this. Hold on. Uh, in test programming, exact programming will not be there. Algorithms will be there. So you may be asked to write algorithms, but not programs. So no need to be very precise about the syntaxes and all. But yes, applications algorithms will be asked. So be ready for that. Okay, I have to put it here. Cool. So what I will do is okay. Let me minimize this and open a new one. Okay. Yes. Let's share. Okay. So we are back at ANSYS. and we'll do a very quick, try to do a very quick simulation. So in order to do simulation for CFD also, we have few tools you can see here, computational fluid dynamics. For that, we have in fluid flow model, you have see 5 types of models we can use. Fluent is one of them. Fluent is the most popular one. And it uses finite volume method. So more into what we did already, what we learned about finite volume method. So the calculations are based on that. Again, we won't be able to very like directly recognize any differences, but things will be quicker as compared to that. CFX, if you see here on uh, the other one. So this one, CFX, is another module in ANSYS, and that works on finite element method. Same things, all the inputs will be same, all the other parameters will be same. However, the again, as I said, the calculations, uh, the way in which the algorithms that are used, those will be different. And even though finite element method covers everything, it does it in a particular way. So if we have a quicker model, then that's why it is more preferred. So Fluent we can use for computational fluid dynamics. And so basically translate computational fluid dynamics in mining sense, we mostly see it as a tool for ventilation modeling, or seeing in underground ventilations, or is any in that sense we can see how our air is moving, or what is the temperature and how the temperature is being dissipated. If there are two or more gases, how they are being mixed, is there what percentage of mixing are there. So all these simulations can be done based on what kind of design we make. Okay. So let's do a very quick. Oh shit! Let's do a very quick design. Or what I can do also is I have done something, so I can show you that. That will be actually better because this takes time. So let's do that as soon as this stops processing. Hmm. So actually, the system that this software is installed on is another system, and that is actually slow. So opening all these modules takes a little bit more time. What system I work on is my personal system. That is fine, but that doesn't have uh, institute license in that. So strange things are happening. Anyways, let's see. Um, it's better, I think, I close this and open it again. That will be quicker. So yeah. So did anyone had any doubts in the assignment for the this simulation assignment? Because we discussed this last time, so I think most of things were covered. But if anyone has anything that we can also take up in time. Okay. So let me, what I will do is let me show you what I did one, and if that works. Uh, right. So in ANSYS, in Fluent, again, the similar things are there. Like for a structural, we saw, right, that there is a geometry component, then we do a meshing of it, then we give boundary conditions and what are the loads and not all these things. Then the main calculations were done, and then we could see the results. Similarly, all these similar modules are inbuilt in this Fluent compilation as well. So disregard the right side for now, but in the left side, you can see there is a geometry. So in geometry, what I have done is I have made uh, an expansion valve sort of. Will show you as soon as it opens. So this is a very simple expansion valve. What we did was we drew a circle in the sketch. If you see the sketch, initial sketch was, I don't know if it is, yeah. So initial sketch was just this cross section, like quarter section of this. One line here going up to the center, the other line here, and till here and back. So this was just the small sketch that we did, and what we did was we revolved it around its axis. So taking the this axis, if you revolve that two-dimensional geometry, you will get a complete full geometry, right? And basically we can mirror this on the other axis and combine them. So we can do this more into how we design the geometry rather than, so it's more like a CAD work than anything to understand in terms of simulations here. But essentially what we want is we have like a small tube that is going into a big tube, and that is again going to a small tube, right? And we what we have done is in on one side there is inlet, and on the other side this will be the outlet. So what will happen when the fluid will rush? It will expand in this expansion chamber, right? And then it will contract to go to the outlet, right? So there will be certain change in velocities, certain change in pressures, right? And that's what we want to see, how what are the changes, how the liquid moves or the fluid moves, and with respect to that, where are the high velocity points, where are the low velocity points, high pressure points, low pressure points, and so on. Okay. So the geometry is not that difficult. Sometime if we have time, we can see how we made this. Uh, After that, what we did was we meshed it. So let me show you the meshing as well. So this is just for seeing how things are done. In our case, when we do for a mine, we can make actually the design of underground sections and say suppose a tunnel cross section and how it goes throughout, right? So we can do that. Uh, okay, so this was our small model. And in terms of meshing, what we did was we just did the simple meshing first. And then we did some changes in the shape and size. So how the meshing will be done and how distributed the uh, nodes were. So that's what was changed by patch conforming. And yeah, that's it. We kept it simple for the simulation purpose. And the important thing was, because we have to define where the water will go or the fluid will go from, and where the fluid will come out, and what are the walls or the friction areas. So in that sense, what we did, we basically named these sections. It is this naming of the sections is important part. So in that, what we do, just we select the faces which we want to name, and we right click and use the create named selections. And in that sense, we basically create an inlet, we create an outlet, right? And we create the wall. So these three names are basically keywords. Like we learned the keywords, right? Computer recognizes what they mean. So inlet, outlet, and walls basically are very intuitive for the program to understand what we want to do there. But still, later on also, if you name it in any other name, suppose A1, A2, A3 or something, that also we can basically change further when we do the when we do the boundary condition uh, assignment. So this was about the meshing. Once we did this, and if we see the next part was the setup or the boundary conditions, material properties, and so on. So right now we are just dealing with the pre-processing stage, right? So in the Fluent setup, it is a little bit different. Uh, so Fluent setup part, the where we do all the processing, is a bit different than the structural part. So because again, all these have their own modules and their own equations that define them. So the way we set them up is also different. So for Fluent, this a screen comes up, and for that we basically choose what kind of precision we want, what kind of simulations these are, and how many ports we want. Like this is the processing part. Like we can do parallel processing, so that will be quicker if we have a multi-core processor or something. And if we just don't have that, then we can use a serial one that takes a little bit more time. Just click OK and see what are the options. I will show you what are these. So this stage is called the processing or the setup stage for the Fluent software. So Fluent is another like a dedicated module here. Like we had the structural mechanical module that we were working on previously, similar here. But this one is for the computational fluid dynamics. Now we have our model here. We have it meshed, and we can zoom in, zoom out, or see how it is, whether it has been rendered properly from the previous modules or not. So now all these things can be done. What we are concerned here right now is few things. First of all, what we need to do, we need to tell the system that which kind of fluid goes inside, right? What are its properties? And we have to tell the system with what velocity or with what pressure it goes in, or any other condition like with what pressure it should come out, or if there is any friction in the wall, so how much friction is there? If there is not, then what are the conditions? So all the boundary conditions, the material properties, all have to be set, right? So those things we will focus on here. So in materials, we have these two kind of areas where we can do. So in fluids, actually, whatever the fluid material will be there, so we can see which are available, and if our fluid is not, we can actually make one. So by default, only one was there. I added this water liquid, and we can add more by double clicking it. And even the Fluent has a big library of databases. So Fluent database has like already pre-fed material library, like all these chemicals are there, ammonium liquid, atomic hydrogen, and like most of the things are which can be used in our day-to-day activities or in our chemical or uh, uh, this fluid dynamics related work. We have those already fed. If not, we can make like externally or give its properties. If we find something that is useful, just click here, like fuel oil vapor. So you will have all its properties. So these are the properties that are pre-fed, and we can use those. So like density, specific heat, thermal conductivity, viscosity, all these things will be required, right? So uh, those are the things that we capture from here. And once we are satisfied, we can just copy it and close it here. So for our case, we had water. So we used water here. And once we have this, so this is like we just define the material, but we have to assign the material as well, right? So in the cell zone condition, that is the assignment part. So in fluid, if we do that and double click it, so it will ask which material do you want and what are its properties. So in place of uh, e- sorry, yeah. So the solid part, it is detecting what is the zone in which you want to fill the fluid. So this is the whole solid. It is considering this body as the solid body. And what will the material name? So in material name, we can give our material that we just selected. So water liquid will be our material. Air was by default, so we changed it, right? And then the boundary conditions, right? So what will be the velocity of the inlet? What will be the properties of the wall? What will be the outlet? So we can all define it here. Like for example, I'll show you in inlet. So we have defined this part, the red portion here as inlet. So in inlet, we can define various modes in which the water can go in. So like for in terms of momentum or the velocity part, we can give magnitude, we can get components. So what I have given is basically absolute velocity of 4 meter per second. 4 meter per second inlet is from this side. And we, if we want to do some thermal analysis, we can do that as well by selecting the models. And if we want to do that, we can set a temperature sometimes here as like 100 degrees Celsius. Or if we want to see if there are two water streams or the fluid streams that are mixing. So those kind of simulations we can do, suppose like in our ventilation part during the defumigation or where the heat is high. So whether our ventilation is actually removing some heat or the temperature is reducing, that all simulations we can do. So if time permits, we will do those. Some examples we'll take. But for now, just I wanted to show how things are done. And like this was the inlet internal properties, or the solid properties we have already defined. We have assigned water to that. And if for outlet, we have to give uh, what is the desired velocity or the pressure that will be in the outlet. So we have just simply given it as zero. Zero pressure means it is an open tap sort of, so it whatever goes in goes out. In sense, we can also give some more higher pressure, and in that way it will calculate accordingly. We can also give other parameters like relative to the boundaries, or even total pressure or static pressure, whatever you want, we can actually give the values and it will calculate accordingly. So these are like boundary conditions, and all the calculations that will be done will be according to that, right? Let's move ahead. I think once we are done with this, we just have to give certain more properties like mm, number of iterations we want. So that will be, I think, here. Yeah. So number of iterations we want to do. So I have given 1,000 number of iterations. So iterations basically, as we or know in these kind of simulations, how many times it runs and sees whether the error or the change in the values is significant or not. And once we do all these calculations, it basically stores the result in the result one. So I'm not doing it right now. So we can actually get good idea of how the things will be. So suppose, for example, I want to uh, right. I want to create first a surface. Okay, something is not right here. But let's start with how the contours can be. So in graphics, we have these options of, I think we have to calculate it again, maybe. Yes. Yeah. So when we calculate, uh, these are the x, y, and z velocities that are residual. So basically, something like as soon as the calculations are going on, it is judging that beyond the threshold that we have given, like for both of the cases, for iterative simulations, we have these two conditions, right? Number of iterations we give and the threshold we give, right? So anything that reaches beyond that, we can do that. Just hold on, guys, till the time it is happening. Sorry for that. uh, okay, what's happening? ये तो हैंग हो गया. तो आइडियली क्या होता है जब हैंग नहीं होता ये, तो these lines basically dip to a certain extent. So हम लोग what we give is the threshold कि the difference between the next velocity should not be more than certain threshold. If it is more than threshold, then you have to do the iteration again, right? So that's the condition for iterative type of calculations. When we either finish the number of iterations or we reach below the threshold, the calculations are done, right? तो ऐसा होता है. Somehow it has hung. Okay. एक काम ये भी कर सकते हैं, इसको बंद कर देते हैं. राइट. तो So whatever was hung is unhung now. I hope. Yeah. So iterations have complete. It, so as you can see, the system is very, very slow. But let's try one more minute to see if we can work it out. Yeah, so now calculations are done. They have basically reached an ideal solution. I think all the 1,000 iterations were done, so that's why it is stopped. So what we can do, we can try adding path lines or polylines. Let's try doing that. Uh, and from the inlet, we go for lines, and what it will define is basically uh, uh, velocity, right? In terms of velocity, we can give. And if we do that, you can see how the uh, yeah. So we can see how the velocities are changing, right? Uh, the smaller portions have high velocities, and while the broader portion becomes pressure reduces and the velocity also reduces. I think if we can overlay the outer boundary, can we overlay the outer boundary? Uh, yeah, we can, but anyways, let's see here for now. We can visualize these. We can actually animate these as well. We can use anything else like line arrows. Uh, in terms of that, oh, that is too much. Size should be even lower. Even lower. Yeah, something else. In terms of line arrow, we can have points. So visualization can be done. I don't know why it's a little bit hodgy sort of here right now. But very good visualizations are possible. Somehow, yeah. So how the velocity changes from start to finish, we can see here, right? This is the part of your inlet is there, and how it goes ahead, how it reduces. These are not actually what I want to show, but apparently we can add contours, we can add other tracks. So let's try what all we can do. Yeah. In terms of contours, we can add surfacial contours. So in like inlet and outlet, we can have velocity contours. And let's see. Oh, it has given in wall. Sorry, I selected wall. Yeah. So in the inlets and outlets, what is the velocity distribution? So outside, we are always considering the frictionless wall. And inside, the highest velocities will be there. I think both can be simultaneously shown, right? Strange. Somehow, I think something is going on in this interface. I will check it out. But mostly all things are generally shown very nicely. We can do some animations as well. We can clip one or two scenes and we can make animations from there. And even after this, there is a post-processing module here where we can do all these things that we were doing in this Fluent in the ANSYS interface, like we did for a structural. But we'll do that later on. Let's do that. For now, let's close it here. Maybe in next few classes we can see more stuff. And yeah, so basic idea of how the fluid flows, what are its change in velocities, in pressure, in if any resistance is there, we can try modeling that. We can see how if the bends are there, so we can try seeing how the bends behave. We have these ventilation equations, right? That whatever the bend will be there, we can calculate the pressure differences and all. So you can try seeing those. Many things can be done in this. And when we design it properly, if we design it on a large scale, a full-fledged ventilation simulation can be very nicely done. And I think we will do it sometime if time permits. Okay. So let's close it for now. Do join that. Are all of you added in? Are all of you added in that session? Any idea? All of your names are there in the departmental seminar team. So the seminars mining underscore NIT RKL. This one is the team. I tried adding most of you, but I don't know if anyone is left. So do enter this. We can. I will start it soon. So do come in this one, and as soon as the guest comes, we will start. Okay. So let's close it in our main class. I will join here. Okay. Thank you very much. Thank you all of you.